Well, hello friends. Welcome back to the program. Today we're going to work on kernel stuff, and I'd like to implement shared writable file mappings because that's a common Unix feature that Serenity currently doesn't support. And I'm not exactly sure how we're going to get it working, but let's just start by making a little test program that we can use for this. We'll call it mcpp. And then we will just start from there. So essentially what we want to do is we want to create a file, memory map it, and then write something to that memory, close the file, and then what we wrote to the memory should show up in the file on the disk. So yeah, let's get started. We'll start by opening a file. So we'll open foo, maybe read write, create, and all the permissions in the world, why don't we? Let's get unistd and fcuntal. And of course, if that doesn't work, let's pair and return so that we know that something went wrong. Because probably things are going to go wrong here. So I mean, since support is missing at the moment. After we open it, we want to ftruncate. So ftruncate fud, let's go to 16 kilobytes. If that fails, ftruncate. Sure. Okay. And then I guess we memory map it. So something like this. Anywhere is fine. 16K to memory map, prot read, prot write, because we want to read and write. And we want to be shared, not private, but shared, which means that the changes made to this memory are reflected not only in other programs' shared mappings of the same file, but also in the on-disk representation of the file. So yes. Okay, if that fails, sure, and then let's write something to it, I guess. So we'll put like a cool X, because X is a cool character, and maybe a new line. And then the rest of it will be filled with zeros. But you know, we can also be good boys and just do that. And then for good measure, why don't we close it? And I think as a first cut, we can support only flushing the stuff to disk when you close. And then we'll also want, what is it called? Msync, right? Msync, to synchronize a file with a memory map. Is that a POSIX syscall, I wonder, or just a Linux thing? I don't actually know. Msync POSIX. Msync is POSIX. Great. Okay. Then let's see. So if that close fails, let's write an error message. Close failed. Otherwise, let's just say something like yoo-hoo, because we wrote the thing out. And actually, let me just let's just test this on Linux, just to make sure that we are doing everything right. So I'd make a little test directory here. Make a little separate copy of it, and that gave us foo. Foo has X new line, and it's 16K. All right, so we are good. Test program looks good, works on Linux. Let's see how it fares on Serenity. So that's called M, not supported. Right, so mmap does not support the combination of prot write and map shared. So our first thing that we have to do is go and I guess, disable that check. So e not sup. No, where is that? Map shared. Is it not called e not sup? I remember this because there was a patch just yesterday or earlier today where we added this failure, not supported, e not sup. Where's the e not sup? So this is a recent thing. Oh, here we are. Ah, okay. So inode file mmap. This is where the error comes. Yes, fix me. Support writing changes made to shared file mappings back to disk. That's the fix me that we are about to fix. So let's get rid of that. And then something that's important to know here is that in the kernel, a file-based VM object is called an inode VM object. And there are two specific subclasses. There's shared inode VM object and private inode VM object. And they correspond to map shared and map private, those two different mmap modes. And a shared inode VM object is globally shared between all processes that map a file into their address space, whereas private inode VM object, as you could imagine, is private. So it's unique to the process that has mapped it. And changes written into a writable private inode VM object are not flushed to disk. They're not supposed to be, so that's fine. But shared inode VM object needs to do something about them. So I'm just thinking, what do we do with this? I guess there are a bunch of different things in play here, because I'm just thinking about coherency. Like what happens if you memory map a file, writable, and you write something to it, but you don't flush it. And then you also do direct IO to the file, so don't memory map it, but use like read and write syscalls. What do those see if you have pending unflushed dirty memory mappings of the thing? Those are all things that we'll eventually have to figure out, but I think today let's just start easy and get something that kind of works, and then we can discover more problems along the way later. Let's not get too ambitious. So so we've mapped this thing writable, but at the moment nothing will show up on disk. So we'll want to have, maybe we should have the sync call immediately, actually. So that will be something like msync. What were the arguments? Address, length, and flags. Okay, sure. Then you can tell it if you want async, sync, or invalidate all cached copies. Interesting. All right. So msync doesn't actually look at the file descriptor, but rather at the address. So something like that, msync, let's say. Where does msync come from? Oh, it's supposed to be an mman. All right. We'll just add it here, no problem. So POSIX sys mman. This will be 1. Async will be 2. And our friend ms invalidate will be 3. Because these are not... oh, wait, no, hold on. The flags argument is constructed from the bitwise inclusive OR of one or more of the following flags. But why would you want to OR async and sync? That's a bit weird. But all right, fine, let's turn them into ORable flags. No trouble. So it says here, either ms async or ms sync is specified, but not both. All right, so it's just a little awkward API is all. Sure. So let's go ahead and add the msync syscall, I guess. We'll put it right under this guy. So error or flat putter says msync, and then we had a user space void star followed by a size t and a int flags. Okay. And we'll put this here. So what does msync do? I guess let's, for simplicity's sake, let's just assume that it refers to a single memory region. So that would be address space. Man, it's been a while since I wrote any code like this. So this will be fun. Address, virtual address, and the length. Actually, length is kind of an awkward name for that. Let's call it size. Also, this is a really neat feature in C-Line, by the way. Just wanna point out something that's neat. So notice how it puts this little inlay hint here that this argument that I'm passing is called size in the function that I'm calling. So this constructor here has an argument size, right? But it's only doing that because the name I'm passing is different. If the name is actually the same in the constructor and the argument that I'm passing, then it just removes the hint. I feel like that's just really neat. So it doesn't say size colon size. Anyway, that's just cool. All right. So if we don't find the region, we will just say enval, whatever. Maybe we could even do find region from range. Oh, that's nicer. And then, yeah, maybe we'll have a is this supposed to support partial? Probably. So like if you pass like the address and length that spans over multiple memory mappings, it probably is supposed to flush all of those mappings. So we probably want to flush multiple, flush all mappings in the address plus size range. But we're not gonna do that right now. We're just gonna do something simple. So then let's see. So then we have to look at the VM object backing this thing. So region VM object. And if VM object is a shared inode, then it's time to do something. So actually, if it's not a shared inode, we can just say, I guess we can just return 0. Let's see, what are the errors? The indicated memory or part of it was not mapped. Blah, 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 blah. So yeah, so let's say if it's not a shared inode, let's just say that it succeeded. And otherwise, let's tell the shared inode VM object we're gonna need to bring in kernel memory shared inode VM object.h. Okay. Inode VM object dot sync, and then we just have to pass in. I was gonna say we have to pass in a range, but for now let's just have like a single thing that flushes the entire VM object to disk. That's a bit suboptimal, but for simplicity, let's just start with that. Obviously, later we want to, like if say that you open a 4 GB file and you write 1 byte, right? You don't want to flush 4 GB of disk writes, but just to get started. So let's see. We'll have sync. Okay, so what's this thing gonna do? Shared inode VM object sync. And then we have a reference to the inode that we belong to, because we don't load everything from disk right away. We load it on demand, right, through page faults. So we do have the inode on hand. Also, we have a bitmap of dirty pages, which I'm not sure what that's used for. Is that actually used for something? Dirty pages set. So, okay, so we copy the dirty pages bits. Wait a minute. Who touches this? Dirty pages set. Oh, nobody touches that. Okay, well, that's funny. So there's sort of the start of a mechanism. I or somebody, or probably me, worked on this at some point, started thinking, oh, we should track dirty pages. But then we don't actually set anything dirty anywhere, so it's not super useful. Also, we could probably move that to shared inode VM object, so it doesn't need to be part of private inode VM object. But that's a different thing entirely. Because a private inode VM object, see, does it care that it has dirty pages? I'm not sure. I guess it's interesting for statistical purposes to be able to show in system monitor that like you've mapped this thing privately and you have dirtied some part of it that will never get written back to disk. But the fact that you've dirtied some of it is a little bit interesting. I'm not sure that this is the best way to track that though, but let's not get off track. So how do we sync one of these boys to disk? I guess by iterating through all of our memory pages that we have in RAM, and then just writing them out one by one to the inode. It's the best I can think of. So at that point, we're probably going to want to lock the inode. So the inode has a lock, which we can take when we want to write to it, which means that nobody else will write to it at the same time. What is it called? Get lock? No? Mutex? minode lock. That's right there. Wait, there's no way for me to grab at that? Okay. Maybe I'm overthinking this. Let's see. What would be the easiest approach here? So let's iterate through let's lock our own VM object. Scoped spin lock, kernel locking spin lock, scoped spin lock. No, what's it called? Spin lock locker. Spin lock locker. That's what I wanted. Get lock, mlock. There we are. Okay. And then physical page in physical pages. All right. So these are the physical pages that we have used to map the file from disk. So because this is lazy, what we do is we create a fixed size array for this memory mapping that has an entry for each page. So every 4 kilobytes, we have a pointer to a physical page. But if you never actually load or write to that part of the memory mapping, then we don't create a physical page for it. So we don't actually allocate memory unless you try to use it. So we have to go through this array of physical pages and check which ones are actually mapped. And then those are the ones that we need to flush back to disk, because any page that is not mapped, it by definition, it will be the same as is already on disk, because we didn't actually fetch it from disk, if that makes sense. So basically, if physical page is null, then simply continue. Otherwise, inode, let's see, can we write bytes? And then we need the offset. Wait, so how does that work? Shared inode VM object maps the entire inode, right? These mappings don't have an offset. Yes, they start at 0. That's good. Okay, so we actually need to know the index into this array here, so we can't just use a range for willy-nilly. We have to track where we are. So let's see, page index 0. Iterate to page count. All right, and then let's say page index. Okay. And then what do we need to provide here? We need to provide the offset, which would be the page index times page size. The size is a page size. Then we need to okay, so this is the part where we need to actually have a pointer to some data that we can use. So this part is a little bit tricky because we probably want to be able to sync this from any context, even if you're not running in the context of the program that mapped the file. So for example, if we have a periodic disk flush service that runs. It's called sync task. I was just forgetting what it's called. It's called sync task. And what sync task does is it just wakes up every couple of seconds and flushes any pending writes to the disk. That's his whole purpose for existing, is that. And I think we'll probably want to do stuff like this from sync task maybe at some point. I'm not completely sure. But say that we wanted to do that, then sync task doesn't have this particular physical page mapped into its address space, because it's all we know is that we have a VM object that has some dirty physical page, but we actually have to map it into our address space before we can write it out. So how do we do that in the easiest way? The easiest, cheesiest way to do it is, and this is definitely not going to be the most efficient way, but we could quick map the physical page. So let's see. Putter. Let's do this like this. And then we'll write it into a stack allocated buffer. I think that will be good. So page buffer. And putter is memory. Wait, how does this work again? mm.quickmap. I forget how quick mapping works. Quick mapping is when you have a physical page and you want to you want to just get it set up with page table mapping so that you can access it, but you don't want to create like all of the usual page table metadata for it. So it's just sort of temporary short-lived mapping, and we have a dedicated quick map page table area for that. So quick map page, that's what I'm looking for. Okay. And that's not good enough because it's a private member of, That's fine. So maybe we should have a convenience function for this actually. So we would do something like read copy physical page. So copy the physical page into page buffer. Memory manager. Yeah, this, I don't know. This feels like a useful helper API here, but I'm not sure if the layering is completely right or the factoring is good. But let's not sweat that too much right now. We will just say copy physical page contents. Copy physical page content. Copy physical page is good. Physical page. And let's take a page buffer. So something like that. It's a little bit of a strange API, but let's try it. And then here we'll take a lock. So quick mapping usually takes there's the lock that guards it. It's the lock, as I recall. lock. Spin lock, locker, lock. Okay, and then auto putter is quick map page, physical page. Oh, it can't be const. All right, that's fine. We can live with that concession. Okay, so now we mapped it, and then we also have to unquick map it at the end here because there's only one quick map slot. So that's why we have to take the memory manager lock, because at the moment we only have one quick map slot per CPU. I feel like it would be pretty sweet if you could have multiple quick map slots somehow, so that you could have like many people quick mapping at the same time without having to take the lock. Instead, this thing would kind of block until it can get a buffer and so on, or a slot. But let's stay focused. And then here now we simply have to mem copy from the mapped page into the page buffer. So quick mapped page size, there we go. Okay, so once we've done that, now I can create a user or kernel buffer for kernel buffer, page buffer. I think that's how you do that. And then we have to pass an open file description, but we'll just say null putter. Because we don't have an open file description in this case. And then this can fail. So I guess we should probably try to propagate errors from here. So we should really make this thing return either an error or void. That seems fine to me. So then we'll just try to do this. And if that fails, we will return the error. So that's good. And then let's check, what did we do here? In msync, we now also have to wrap this in try, of course, because now it returns an error or. So it is a compile time error to not propagate errors that happen. So there we go. Now, of course, I didn't actually set up the msync syscall with a wrapper or anything. I also didn't add it to the list of syscalls. So we're gonna have to do a bit more than just that. Let's see. Here's the big list of syscalls. mmap. Let's just go ahead and these are going to be alphabetically ordered, so just have to take care of that. But let's just start by oopsie doopsie. Let's just do that to alphabetize. Okay. And we also want to add in mman.h, we need to add msync. So msync, what was it? What was it? Void star size t and int. All right, so that should be it. Now we have to rebuild a bunch of stuff, but then should be good. While that recompiles, I can write the libc wrapper for the system call. So that's just a plain rc syscall sc msync address and size. Address size flags. Yeah, just the usual errno transfer. Okay, and then the flags argument. Oh, I'm not doing anything with that. Well, for now, let's just say it's not used. That's okay. It's not like we have sync or async implementations here. We just have this one synchronous thing that writes that flushes the entire thing. So. Okay, that built. Interesting. Let's see if it works. So yoo-hoo. All right, so we got a foo file. It's cat foo, and it has the X. That is neato. And it is indeed 16 kilobytes. So very, very cool. Oh, hex dump. We need to teach hex dump how to coalesce these repeating lines. But yeah, it actually came out perfectly nicely. So that's super sweet. I think, let's see. So say that we didn't msync, right? If we msync, then this works just fine. But what if we just close the thing without msyncing? Then this is just gonna we're just gonna lose those modifications because we do them in msync. So I'm thinking, as a simple first cut, completely unoptimized, what if when we tear down the shared inode VM object, we can just sync it, like write everything out. if it is writable. It's definitely not optimized, but it should get the job done. So first we have to remove that, of course. So now we say yoo-hoo, but if we cat foo, it doesn't have the X new line that we put in there. So I think in order to make this work, I feel like the simplest thing we could do is to just, like we could write it out in the destructor, I guess. Although that does feel a little bit shaky. I don't like doing things in destructors, certainly not complex things like that. What's that thing that we have? We have something like something that gets called before the destructor. I forget what it's called. There's some magical thing about, no, what the hell? Will be destroyed, is that the thing I'm thinking of? Will be destroyed, yeah. So if we add a will be destroyed, then it will be called before the destructor is invoked. And then we can do stuff a bit more casually. So let's see. I guess in order for that to work, we have to add will be destroyed at the base class level and make it virtual. So let's see, will be destroyed. Something like that. And then shared inode VM object can have virtual. Actually, let's make it public. Will be destroyed. Override. Sure. And in shared inode VM object will be destroyed if, how do I know if I'm writable, actually? I guess I don't know if I'm writable. Oh, damn. Right. The VM, this is the wrong level to put this, because the VM object doesn't know if it's writable or not. The individual memory regions that are windows onto the VM object, they know if they're writable, but the VM object doesn't care if it's writable or readable or executable or whatever. It's just a virtual memory object with some data that it can fetch for you. So this needs to go in region. So region CPP, let's see. In this case, regions are single owner. So we can do stuff in the destructor here because it's like a lot better controlled. So what's the thing that we want to do? We want to sync if this VM object, if we have a VM object that is a shared inode VM object, then we need to sync it. Yeah. So let's say if is writable and VM object is shared inode. Yeah, let's do it this way. This is not super beautiful, but it'll get the job done. This is very aggressive. Find a way to do less work. To only do what's necessary. To defer the, to only flush what's necessary. Find a way to do less work. That's really what we want to do. Because there are multiple strategies in doing less work here. Like we can defer the flush instead of doing it synchronously. So we can like just mark the BM object as dirty, for example, or something like that. And then have a periodic thing that goes and takes care of it. We can also keep track of which pages have been touched. The MMU can help us with that. So we can, for example, we can set the write protected bit on the page table mappings. And then, when we get a page fault, we can just say, oh, well, this has a PV bit set, but we only made it write protected so that we would know if somebody wrote to it. And then we will update our dirty bits internally based on that. But all of that is more advanced optimization topics. So today we're just going to make something that works, and now we have something that will hopefully kind of work. We are going to have to just swallow errors here. This may fail, right? But we don't really have a way to propagate errors because we are in region teardown. So for example, if the program crashes, we just have to unmap all the memory. But there's nobody to return that error to. So we're just going to have to drop it on the floor, basically, if the sync fails. Tough luck. I sometimes wonder if it would be interesting to have sort of some kind of mechanism for collecting these errors that get dropped on the floor, because there's no propagation route at the point where the error occurs. You could have some sort of like an error catch-all error mechanism in the kernel, and then it would maybe just write out the error to syslog or something. Because it always feels bad to drop an error on the floor, but we simply have nowhere to put it, so it is what it is. So remove foo and then run m cat foo. And now it gets the X, because when we exit the program, or when we exit the program, we tear down the region. It should also happen if we unmap the region, but yeah. So actually we can easily test that by just doing something like, which is not close, and then we will sleep here. But unmap it. So this should also write it out, because when you unmap the entire region, then it will the region will be destroyed. We will flush the changes to disk, and they should show up. So in this separate window, we can see that indeed they have been flushed. Very, very cool. All right, so let's do commits. So what did we change? We added msync, and so we added msync. These are flags for msync syscall. We added copy physical page, a helper for quick mapping a page and then just copying out the contents. Let's do that as a separate commit because that's nice and self-contained. Kernel, add memory manager, copy physical page. This is a handy helper that copies out the full contents of a physical page into a caller provided buffer. It uses quick mapping internally. And so it required to take and takes the lock while doing for the duration. Yes, that's cool. And then the sync mechanism, sure. So I guess we can add the msync syscall first of all. So we don't need that change, don't need that change. kernel plus libc add msync system call. This allows user space to trigger a full flush of a shared file mapping to disk. Note that shared file mappings are currently not possible since mmap returns e-not sup for prot write plus map shared. That will be that restriction will be removed in a subsequent commit. Actually, let's expand on that a little bit. We iterate over all the mapped pages in VM object and write them out to the underlying inode one by one. This is rather naive, and there's lots of room for improvement. Yeah. Okay, and then let's support writing changes. So let's remove that fix me. Kernel remove or allow mmap with prot write plus map shared. Now that we have a way to flush changes back to disk, let's allow this functionality, this type of mapping. And then let's also do the implicit thing. So kernel automatically sync shared file mappings on region teardown when unmapped. Yeah, so to make sure we don't lose changes, memory regions that shared file mappings will now be fully synced when they are unmapped, whether explicitly or implicitly via program exit. By the program exiting, crashing, etc. This does a lot. This can incur a lot of work since we don't keep track of which pages actually don't keep track of dirty pages. But that's something we can optimize as we go, or optimize later, or optimize down the road. Down the road. All right. So I think that's basically as far as I wanted to get the feature today. So let's check it out one more time. And actually, let me re-enable this stuff. But yes, That's pretty cool. So that was easier than I was expecting. Of course, what we've done is very naive, but it should be pretty straightforward to make this more sophisticated. But that's a topic for another day. So I'm gonna end the video here. If you made it this far, then I thank you for watching. I hope that you saw something interesting today. I'm pretty pleased with the outcome, although it feels very naive, but you have to be willing to do things in a naive way to get started, because every journey starts with a small step and all that. So thank you very much for checking out this video, and I will see you next time. Bye.